Now we're going to look back at a concept we talked about earlier in this class, but we're going to give it a more formal definition this time around. So when we first talked about continuity, we said you could imagine a graph, and if you can draw the entire function without ever taking your pencil off of the paper, then it would be described as a continuous function. And a discontinuous function would be what happens if you're drawing the line and at some point along it, you have to stop, take your pencil off the paper, and then continue drawing it again from somewhere else. So this was our definition of discontinuity. Here's where you're seeing our more formal definition now. So the three conditions that have to be met for a function to be continuous, especially if they say continuous at a specific point, otherwise this has to apply everywhere on the function. The first one is that the function must be defined at that point. So you can't have a gap in your graph. There can't just be a hole hollowed out and there's no answer for when x equals 3. Second condition is it has to have a limit for the x value of that point. So when you're looking at x equals 3, for example, when you evaluate the limit by looking at the numbers really close from the left and the right hand side, so 2.9999999 and 3.0000001, there has to be a limit answer that you get. You can't get the limit does not exist because it doesn't match from the left and the right hand side. And then the third condition is that whatever that function was evaluated at, whatever the dot on the graph was, that has to be the same answer as the one you get from taking the limit of the function. So the short summary in math terms is basically that the function is continuous if and only if you can plug in a number, like plug in x equals 2 and get a y value, and that y value that exists has to be the same answer as what you get from taking the limit of the function at that same x value. Here's some quick examples to show you what continuity and discontinuity look like. This function is continuous because if I picked any point on here, like let's say x equals -3, if I find the y value, it looks like it's hitting a height of about 3, maybe just a little bit below, but there is a y coordinate for that location. If I took the limit from the left-hand side, it seems to be leading to that exact same coordinate. There isn't like a weird jump or having it go to a different direction. From the right-hand side, the limit seems to be hitting that exact same point. So sure enough, the point exists, there is a limit of the function, and the limit is equal to what the function is defined at. And that's true for any point along here. Here's an example of discontinuity. Yes, the point exists. If I said when x equals -2, it looks like it has a height of +1. But if I take the limit from the left-hand side, I'm getting a height of 1. If I take the limit from the right-hand side, I'm getting a height of -1. So the second bullet, it must have a limit, fails because the limit from the left does not equal the limit from the right, which means we would say the limit does not exist at x equals -2. Now here's the trickiest case you'll see, because technically this graph is defined when x equals -1, it looks like it equals 3. So the first condition was met. The second condition is that this function does have a limit. If I take the limit from the left-hand side, it looks like it's hitting a height of 2, and the limit from the right-hand side looks like it's hitting a height of 2. So since the number matches from the left and from the right, it does have a limit, and the limit's 2. But the third bullet says that the function, which was 3, has to be the same value as the limit, which was 2. So since those two things are not equal to each other, this one is discontinuous. And you should be able to tell graphically, it's easier to tell, just by noticing that there is that weird gap in the graph. Now, like I said, looking at it from the graph is usually fairly easy, but I also need you guys to be able to do this algebraically because maybe you won't have access to a graph or you won't have access to graphing technology. So the way you will determine if functions are continuous for most of the assignment is by assuming the function is continuous and then looking for one of these bullets to prove that it's discontinuous instead. The first bullet is, are there any values of x that make the denominator of a function 0? So if you have a fraction, check to see if there's any answer for x that would make the function undefined. If so, that's where the discontinuity occurs. Next is, where are any values of x that aren't defined in the domain? This happens a lot with piecewise functions, where maybe they'll say one function is used for all the x values less than 0, and another function is used for all the x values greater than 3. Well, then there's a big gap for all the x values between 0 and 3, and that would cause a problem. Another example would be something like a square root. Remember that you can't have a negative inside of the square root, so that kind of stuff can cause a discontinuity. And then piecewise functions that don't meet at the same coordinate, maybe there isn't a gap in the x values. Like if one of them says for all the x values less than 3, and the other one says all the x values greater than or equal to 3. So there's no gap in the x's. Every x number is covered, but you want to make sure that the function on the left-hand side hits at the same height as the function from the right-hand side. And then there are some functions that are just always discontinuous. This one is the one that creates that ladder step function looking thing where you have open circles on one side, closed circles on the other, and it's just a bunch of different little steps all the way through. So now let's look at some of the examples that you'll have in the math lab assignment. This one says to use the definition of continuity to determine whether the function is continuous. So starting off, if I'm going through my conditions, I'm going to assume this is continuous. I don't see a fraction, so I don't have any of the denominators that I have to worry about. It is not a piecewise function, and it does not have any restricted domains on it, nor is it one of the special functions like the step-ladder function. So if you're looking at the bullets we listed, it passes every single one of these, which means we are going to assume the function is continuous. And that's going to happen for a lot of them. Usually functions are continuous unless you have some of these weird things happening like fractions and piecewise. So for this one, you can say the function is continuous at 4. You could also confirm it by evaluating f of 4, so plugging 4 in for x, and then finding the limit at 4 and determining that those two things are equal to each other. Here's an example where we do see a discontinuity in it because we're asked to evaluate this at 13, and the problem with plugging 13 in is that makes the denominator of the function equal to 0. And there's no way for us to cancel this out because we don't have any factoring steps we can use on x plus 13 or x minus 13. So there's just no way to get around this. And that means f of 13 does not exist. It's not on the graph. For this example, we have that the function is defined when x equals 4 and it equals the height of 9. But to find the limit, we would care about the numbers where it doesn't actually equal 4. We'd be looking very close to 4. So I need to test that into this equation. And if we factored the numerator, then we would have x plus 4 times x minus 4 over x minus 4. And then those x minus 4 pieces would cancel out. So what I'd be left with is x plus 4 for plugging in the value of 4. The problem is the answer I'm getting from that is actually equal to 8. So the limit would be hitting 8, but the function is actually defined at 9. So since the limit and the function evaluation do not match, they're not equal to each other, then this one would be discontinuous. Here's another piecewise function that has 3 different pieces on it. So the first piece is for all the x values less than or equal to 0. And if you were to plug in 0, because we're interested in like where these two graphs overlap at the certain x values. So at x equals 0, this one is going to hit a height of 4. For this one, it's hitting at a height of 4 all the way across from x values of 0 up until you hit an x value of 4. So they do meet at the same height. They both meet at a height of 4 when x equals 0. So that's good. When we get to the other x value, this one stops at 4, the other graph starts at 4. We know that this one is a height of 4. For this one, if you plug in 4, you get 16 plus 5, which is equal to 21, which is not the same height. So this graph breaks at a height of 4, which would mean we say it's discontinuous when x equals 4, because that's where the jump in the graph is happening, that x value. And for the last couple examples, they're going to give you a function like x squared over x. The first thing you want to be able to do is pick the correct graph of it. Well, if you canceled an x from the numerator and denominator, then this would just be y equals x. And so hopefully you remember from your slope-intercept rules that this basically makes a diagonal line going up and to the right. In the second part, they ask if there's a point of discontinuity at 2. So whether you're looking at the graph or whether you're looking at the function, the question is there a problem with plugging 2 into this equation? And 2 is not a problem. The problem would be plugging in 0 because it would make an undefined function. It would create a 0 in the bottom of the fraction. But plugging in 2 is no problem at all. So is there a point of discontinuity? No, not at 2. And then the last part of the question says there is a point of discontinuity at 0, but they want to know if it's removable or non-removable. Removable means that you can cancel it out in some way, which we said we could do. We said we could cancel an x from the numerator and the denominator, and then our function would just equal x. And if I'm plugging into that function, then plugging in 0 doesn't cause a problem. So that's what we mean by a removable discontinuity. If it was non-removable, then there wouldn't be a way for me to cancel out that denominator that causes a problem. So in this case, since it can be canceled out and then you can plug in, it's a removable discontinuity. And that hopefully will be enough to get you guys through the assignment. So I hope those notes were helpful for you guys. Thank you.